So this chart has been shown. We released the Twister iterative MapReduce, that version 0.9 2 years ago. And we keep that to fix bugs and improve the variety of features. So you can download from the website and provide it on the tutorial website. Typically, to summarize these features, this distinction between static data versus the variable data. So when you look at the application algorithm, it's all about data structure. But we classify this kind of a data. One type is that the raw data is static. You just load it once. It doesn't change over the iterations. Another type is the global data or local data. It changes over each iteration. So that's very important for you to understand the data model. Also, we run it in between iterations in order to make it speed up. So we run long-running MapReduce tasks, not spawn every time. We use a pops-up messaging system to link different components together in the systems, including using ActiveMQ or Narada broking systems. And current release open source is 0.9, and we're actually working on the beta version we will release very soon. Looking at the whole scope of iterative MapReduce frameworks, we can see a lot of state-of-the-art systems. So our system is a Twister, but there's a sister project at Microsoft called Daytona, has been released last year. And the structure is almost similar as a Twister, but it's running on Azure systems. And tomorrow, Selena will talk about Twister for Azure is another version of MapReduce, iterative MapReduce systems on Azure Cloud. Hadoop is a system built on extension of existing Hadoop by University of Washington. And Spark is an iterative MapReduce and support resilient fault tolerance, in-memory fault tolerance by Berkeley. Prego is probably you already heard of that, is Google's MapReduce system supporting graph processing. And Mohood is an extension on Hadoop. It's an Apache open source project to support data mining algorithms. I can go on this for a lot, but I list a lot of other similar works, but they target different kind of optimizations. So the ultimate goal is that we try to build a runtime system so they can support data analysis and processing, but also run on different kind of platforms, including HPC cluster, commercial cloud, all these kind of systems. Ultimately, we want to support software as a service. How do we analyze MapReduce systems? And when you have a problem, which approach you want to choose? I think that is a fundamental question, because after you learned so many technologies about MapReduce. So this is the classification of applications and the patterns. So on the left-hand side, we can summarize that into map only. Basically, you have individual jobs and running in map tasks. So you can scale it out and schedule those. There's no communication between these computations. One powerful function of MapReduce is that you have the framework of parallelism, but then you can integrate it with legacy code. For instance, you have a histogramming program which is implemented in C. You can directly using that library. So that immediately makes legacy sequential code parallelizable. And you don't need to change too much. You just need to integrate that libraries. The second column you can see is a typical MapReduce pattern that is illustrated many times today by word count. So any kind of application, if you can abstract to this kind of a word count type, you can feel comfortable, you can use MapReduce. And on the right-hand side is a class of applications running on HPC or supercomputers, and people familiar with in this field is MPI. And in between them is what we're doing is called iterative MapReduce. So on the left-hand side, you can see a lot of applications that's data parallel, placement parallel. And in the middle is classic MapReduce. On the right-hand side has a lot of linear equation or those kind of loosely coupled applications. So we're targeting for data mining algorithms in the middle, and I'll give you a demonstration of two algorithms. So hopefully, by using iterative MapReduce, we can get the best of the both worlds. That is, that support fault tolerance, like MapReduce, but also have more expressiveness to support richer applications like MPI. So I will give you 2 examples of a parallel data analysis using Twister. One of the algorithms is called multidimensional scaling. Another one is called clustering, exemplified by Kmeans algorithms. So this is actually a demo I will give later on. It illustrates that how we utilize Twister as an iterative runtime system to support this kind of complicated dimension reduction algorithms. This snapshot actually is the result that out of that 100,000 protein sequences have been processed and reduction at the dimension and visualized using our visualization tools. The second example I will give you is a data-intensive K-means clustering on image data. We all know that clustering algorithm is very general and powerful, but there is one class of application is classify images. This is challenging in several dimensions because of the large of the data size. Because we give example is 1.5 terabytes. But not only the size of data and the complexity of data, because the dimension is 500 features. And unlike that, is kind of an example K-means algorithm, they always ask you to cluster and find 10 clusters. This real application asks us to find 10,000 clusters. So that immediately imposes a challenging issue is that we have to create that each of the map tasks and to host the clusters with 10,000 cluster centroids. And that will give a 1 gigabit of a data size, which implicitly asking us to transfer per map task 1 gigabyte of data. So that's hugely challenging for dealing with this kind of a data set. So we got the motivation of doing iterative MapReduce to accommodate all these kind of challenges. And this is the Twister programming model. You can see in the top level is the main program. You set up these kind of configurations. And then you spawn the map and worker nodes so that they can run map tests and the reduce tests. In the middle is the control flow. You can see that you have a classic map and reduce, but the iterative through different kind of conditions, either converges or the number of runtimes. So in terms of the design features of Twister, because there are a lot of iterative frameworks, the unique part is that we have static data loading only once for efficiency, because currently Hadoop MapReduce is that each time they load data from disk and write back to the disk. So what we're doing is that we load static data into memory and do memory kind of a computation. The second thing is that, as we mentioned, that we use long-running thread and it's cached. On the right-hand side, we have a lot of communications. We're not only using classic like HTTP download, but we'll also use direct TCP to accelerate the data transfer in the intermediate stages. And we combine that map and reduce on 2 stages, try to reduce the transfer data size to accelerate computation. We also support fault tolerance.